Hi and welcome back to Gaffy's Grinds. My name is Mr. Gaffy. A quick reminder what we're doing. We are going through some junior cycle science. You're on video 4 of the series on particles. So we're taking topics from the particles modules. We're breaking them down, trying to help you understand them a little bit better, and we're going to give you some practice to do. Okay, so quick reminder, some tips on using the videos. Okay, just try and eliminate any distractions because they're going to stop you from learning. So put your phone in another room or turn it off at the least, and close any other tabs you have open that might distract you on your computer. And most importantly, I'm going to give you tasks and questions to do. And when I do give you tasks and questions, it's really important that you do them. Otherwise, you're not going to learn much from these videos. Okay. So quick reminder again, this is Particle Series Video 4. If you have not watched videos 1, 2, and 3, you should go and watch them first. Otherwise, this is just not going to make as much sense. So it's really important that you watch them in the order that I put them up. Now, in our previous video, we were looking at the 3 states of matter. So if we have diagrams like this, so we've got beakers. So I've got a beaker and I've got 3 beakers. And in these beakers, I've got these 3 substances. Okay, so what do these 3 beakers represent? So I want you to tell me on 3, what do the 3 beakers represent? So on 3, 1, 2, 3, speak your answer to the screen. Okay, I'm hoping that you said they represent solids, liquids, and gases. Okay, so this first one here would be a solid. Second one, a liquid. And third one, gas. Okay, now if I asked you then to tell me how would we go between them? So how would we go from a solid to a liquid? What would we have to do to get that change to happen? Okay, so on 3, 1, 2, 3. I'm hoping that you would have said we would have had to add energy. Okay, add energy by heating. Now when we add energy by heating, we add energy to what we call the thermal store of the substance. So we add energy. Add energy by heating. And when we add enough energy, we can get the substance to turn from a solid to a liquid. Now, how do we get this substance to turn from a liquid to a gas? Diagrams represent what we would see at the macro level. What we mean by macro level is stuff you can see with your eyes. That's what those diagrams represent there, okay? What you can see at the macro level. When we're talking about chemistry though, we're talking about what you can see, how we can understand what's happening at the micro level. So stuff that we can't see. So if we were to start again and draw the containers and draw what's inside substances. So I've got my 3 beakers again. Okay, and I'm going to draw, what do the particles of the solid look like? Well, we would expect to find something like this. Okay, and in the liquid, five, 6, 7, 8. Now what I'm doing is I'm counting the particles. 9, 10, 11, 12. So 4 fours is 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, why was that important? Why is it important that I show that there are the same amount of particles here, even though now it's a liquid? Well, it's important because when we do a change, when we get it to go from a solid to a liquid, we don't destroy any of the particles and we don't create any more particles. So that's it's a really important rule in chemistry. in understanding when things change from one form to another, or when they undergo a chemical reaction, or what this is here. This is a physical change going from a solid to a liquid. We don't destroy any atoms. We don't change the atoms. They're the exact same. The atoms themselves. But obviously, there are some differences here. They don't look like they're in the same structure anymore. But that doesn't mean that the atoms themselves have changed. And then the atoms of a gas, or the particles of a gas, we still have to have 16 particles. One, two, three, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay, 16. Okay, so again, these are the solid, liquid, and gas. And again, I'm just going to use these two words again. So up here, this represents what we call the macroscopic. This is what we can see with our eyes. So we see solids generally as lumps of things, okay, and they keep a regular shape. So if you put a block of iron in a container, it's going to stay a block, okay. If we put a liquid in, it typically tends to, behave like a liquid. It takes the shape of the container. And then if we take a gas, generally, you might not even know the gas is there unless it's got a color. Of course, it is there, but you might not necessarily be able to see it. But those are things that we can see with our eyes, the macroscopic level, okay? The microscopic level, we can't see with our eyes. We can't see the particles. So what's inside? What's inside are stuff you can't see, okay? But the explanations help us to explain why we can see the things we can at the macroscopic level. Can't see them, but they help us to explain. Now, of course, if I was to ask you again, how does it go from here to here? From solid to liquid, it's the same thing, adding energy. And going from here to here is adding energy. Okay. The question is, why do we need to add energy? What keeps the particles in a solid together? What keeps them in this arrangement? If I was to ask you what the arrangement was from the last video, how do we describe the arrangement? I want you to tell me, how are the particles in a solid arranged on 3? 1, 2, 3. Okay, I'm hoping that you said they have a regular arrangement. That means they are in a repeating pattern, rows of 4 here. Okay, and they are all very close together, and they are all touching. Well, why is that? What keeps them together? Well, the correct answer here is something that we refer to as interactions. Interactions between particles. And generally, these are interactions that are attractive. That makes them want to, they attract to each other. It makes them want to stick together. So interactions between particles keep them close together. Now in a solid, the interactions are at their strongest, which means that all the particles are kept in rigid rows, all really tightly packed together, okay? And the particles at this stage have their lowest amount of energy. So the interactions are really good at keeping them tightly packed together. Now when we add energy, of course, we're adding energy to the thermal store of these particles, or we're adding energy, thermal energy to them. And what that does is it makes them move more, it makes them vibrate more. And we've seen in the last video again, the motion lines that we put around particles to show how much they're moving. So when we add energy, it goes to the thermal store, and then from the thermal store, it moves to what we call the particles kinetic store. And the word kinetic just means to move. So that makes the particles move more. And as they move more, what that does is it helps them to break or overcome some of these interactions between particles. So when we've added energy, we say sum of the interactions. Some people say broken here, but I think there's a better word here, is overcome. There's enough energy to overcome them so that they don't become as important anymore. Okay, so some of the interactions between particles, are overcome. That's what's happened when it's turned into a liquid. Now, this process where the interactions are overcome, okay, is what we call melting. Again, we saw that change of state in the last video. Solid to liquid is called melting. And what's happening when melting is happening is that the energy that's being put in is being used to overcome some of the interactions between the particles in the solid. So this makes them some of the particles are a little bit more free to move around and be able to change positions with each other. And that means that they're not in nice, neat, straight rows anymore. Melting. That's what melting is. For different substances, this happens at a specific temperature. Okay, so for water, for example, this happens at 0 degrees. So melting happens at 0 degrees. So there's enough energy in the particles at 0 degrees to overcome some of the interactions between the particles. And this is what causes it to turn into a liquid. We call this specific temperature, we call it a melting point. Again, it's really important to note that different substances will have different melting points. And that's because different substances have different strengths or different interactions between the particles. So different substances have different interactions between the particles. So need different temperatures to make them melt. Now, what happens when we get to a gas? Okay, so what happens? Describe the particles, the arrangement of particles in a gas. On 3, describe the arrangement of particles in a gas. 1, 2, 3. Okay, well, I'm hoping that you said that there is no particular arrangement at all. They are very spread out, very far away from each other, and they are moving very fast in all directions. So at this point, all interactions have been overcome. So we've added enough energy so that all the interactions between the particles have been overcome. This process where we add enough energy to overcome all the interactions between the particles is called boiling. Okay, and the temperature that this happens at, again, it happens at a specific temperature for a certain substance. Specific temperature. And we call that specific temperature the boiling point. So the boiling point of a substance will be the temperature in which all the interactions have been overcome. And again, it will be at different temperatures for different substances. It depends how strong are the interactions between the particles. Now, very quickly, if I was to ask you, give you this scenario, what happens when I take a beaker and I put an ice cube in the beaker and I put it on a tripod stand over a Bunsen burner? Does the ice melt? Yes or no? On 3, 1, 2, 3. Okay, I'm hoping that you said yes. The ice does melt when we heat it over a Bunsen burner. Second question, does the glass of the beaker melt? On 3, 1, 2, 3. The answer to that is no, it does not melt. And what about the tripod stand that's made of iron? Does it melt with the Bunsen burner? On 3, 1, 2, 3. Again, the answer to that is no. So why does the ice melt, but not the beaker or the glass? Well, of course, to answer this, we have to understand that the ice is water, and the glass and the beaker or the glass and the tripod are different substances. They're not water. So the beaker is made of glass and the tripod is made of iron. Now, the answer here is all to do with this over here, the interactions between the particles. So the interactions between the particles of the iron and the glass are much stronger than they are in the ice, and they need more energy to overcome them. Okay, so you have to add more energy to break or overcome those particles and give the particles enough energy so that they can move apart and behave like a liquid. Okay, so that we say that those substances have a higher melting point. They have a higher melting point. So glass has a higher melting point than water, and iron has an even higher melting point than glass or water. Okay. Now, what about the temperature? Why does boiling require more energy than melting does? Why do we have to keep adding energy? So we saw if we add some energy, we can get it to melt. We have to keep adding more energy to get it to boil. Why is that? Well, the answer to that question has to do with the amount of interactions you're overcoming. For a liquid, the answer, or the word here, is some. Some of the interactions between the particles have to be overcome to turn it into a liquid. For gases, to turn a substance into a gas, you have to overcome all of the interactions. And of course, this requires more energy for that to happen. Okay. All right, time to do some practice. So your practice copy is out, and we're looking at the substance water. So question 1 is shown here down below. Okay, I'm just going to pause the video and make some more space for it. Give me 1 second. Okay, so just actually before we do the questions, maybe it's a good idea just to take down a couple of those keywords. So the 2 really important keywords from today are melting point. Melting point. So what is the melting point? Well, we've already seen that the melting point is the temperature. So the point bit means the temperature. So I hope that this is clear. Just very quickly going to draw it again. We've got melting point. It obviously refers to melting in some way. Okay, melting is turning from solid to liquid. That's what happens at melting. But obviously we're not asking what melting is here, because that would be just melting. This is melting point. What we're talking about here is point refers to a temperature. So it's the temperature at which something turns from a solid to a liquid. Okay, the temperature at which a substance changes from a solid to a liquid. Okay, and boiling point then, in the same way. Boiling point is the substance, or the temperature, sorry, the temperature at which a substance turns from what happens at boiling from a liquid to a gas. Now, a concept that's very important to understand is that, no, it's fine. Well, sorry, I won't go into that now because we'll be covering that later. So just practice now. We've got questions 1 to A to G here. So I want you to pause your video and complete them questions now, please. Okay, so you should only be now watching the video if you have attempted those questions and you have really had a good go at them. Again, just a reminder that if you don't practice these questions, you don't have a go at them, unfortunately, you're just not going to learn as much, if anything, in these videos. Okay, so coming up then are the answers. There they are. So pause the video now and make any corrections that you need to make. Notice the way that I've used full sentences. That's important. It's an important skill. It improves the quality of your work. So just pause the video now and make any corrections that you need to. Okay, so we're going to move on now. So you can use these temperatures in a number line to work out the state of a substance at any given temperature. Your teacher, that's me, will model how to do this. Okay. So room temperature is an important temperature to remember. Okay, the average temperature that we consider for most rooms is 21 degrees. Now that doesn't mean every room in history ever is going to be always 21 degrees. Sometimes it's going to be a little bit hotter, sometimes it's going to be a little bit colder. Your home is going to have temperatures maybe a bit above this, a bit below this, depending on how you set your heating, whether you have a fire on, whether your heating's been on in the last few minutes or not. But on average, it's going to be 21 degrees. So that's kind of an accepted figure we take as the average. Okay, we've got a substance, ethanol. Ethanol is alcohol. It's the alcohol you find in alcoholic drinks. It's a colorless liquid like water at room temperature. Well, I'm after giving you the answer, but how would we work it out if you didn't know? So all I'm telling you is the name, ethanol. Ethanol has a melting point of minus 115 degrees and a boiling point of 78 degrees. They want us to find out what state ethanol is at room temperature. Okay, so I'm going to show you how we can use a simple number line to work this out. Okay, so you guys will get a ruler, and on your page, you take your pen, and we'd start and we just draw a simple number line. Now, we all know how to draw a number line, I hope. Okay, so you should know that from maths at primary school and certainly at secondary school. Okay. So what we're going to do is we're going to draw a number line, and on the number line, we're going to put two dashed lines. Okay, so just here, I'm going to put a dashed line like this, one there, and I'm going to put another one over here. Like this. Okay. Now, the number line is going to show us the three phases of the three states of matter: solid, liquid, and gas. Now, the great thing about this is we can do this for any substance, okay? Now, this line here represents, obviously, if it's between solid and liquid, what happens to turn a solid to a liquid? Okay, so go from a solid to a liquid, what do we call that? On three, 1, 2, 3. We call that melting. So this line here represents the melting point. Now this here shows us going from a solid or a liquid to a gas. So what do we call that? Going from a liquid to a gas. On 3, 1, 2, 3. We call this boiling. So this here is the boiling point. Remember, what is a boiling point on 3? 1, 2, 3. I'm hoping you said it's the temperature that a liquid turns into a gas. So the point bit means the temperature. So these lines here, this is a number line. Remember, these lines will show us the temperatures at which melting and boiling occur. So I need to go to my question now, check my question, and look for important information. Well, it says here, ethanol has a melting point of minus 115 degrees. So I'm going to put that on my number line. This is my melting point. I'm going to put minus 115 degrees C here. Okay. And it has a boiling point of 78 degrees. So boiling point, 78 degrees. Okay, C. Now I'm just going to use this number line to point something out to us. If we're going from a solid to a liquid, so going this way here, when we get to the melting point is when it then turns into a liquid. So it's a solid until it reaches the melting point, and then it turns into a liquid. And then it stays a liquid all the way up to the temperature that it reaches its boiling point, 78 degrees, and then it turns into a gas. Now, what I don't have written here on this is what would happen if I was going the other way. What would happen if I was starting with a gas and cooling? What temperature would it turn back into a liquid? Well, funny enough, it's that same line. It would turn back into a liquid at the boiling point. So the boiling point actually shows the temperature that the liquid will turn into a gas, but also the temperature that a gas would turn back into a liquid. And it would stay a liquid then all the way back down to the melting point. At that temperature, it would turn back into a solid. Now, that's a really important point that we're not really discussing in this video. We're only discussing melting and boiling. But those temperatures also work for the other way. That's something that's important to point out. Now, I'm going to get rid of that just so the diagram stays tidy. Now, the last thing, remember, what we're going to do is we're going to, right up here, I'm going to put in a box, what is the temperature? Well, it's ethanol. This is the number line for ethanol. Why is that important? Well, you're going to be doing a few of these in a minute, and it's important that you just keep track of what substance you're talking about. So I'm talking about ethanol. So I'm going to put that in red. I'm going to get a different color then. And the last thing I need to do is plot the temperature that they've asked us about on the number line. Well, they've asked us, what state is it at room temperature? Now, room temperature we learned was 21 degrees C. So I need to find out where is 21 degrees C. Well, the melting point is minus 115 degrees. That's below 21 because it's a minus number. It's well below 21. The boiling point is 78 degrees. That's above 21 degrees room temperature. That means room temperature is in here somewhere. So I'm going to put here 21 degrees room temperature. Okay, so that answers the question for us. That proves for us that ethanol is it's in the liquid part, so is a liquid at room temperature. And that is how I do that. That's how I find out what state a substance is at room temperature. Okay, so you'll go now, practice a few questions. Okay, so there's going to be 5 questions for you guys to do. Okay, see them here, questions 2, 3, 4, and 5. Zoom in a little bit more, so they're a little bit bigger for you. Okay, and the first 4 are number lines like we just did. Okay, and the next 2 then are just some questions from memory. Okay, now if you feel like you need to take my one down as an example, I'm going to just put it up for you there. Okay, so if you want to pause the video and take that down, you can. Okay, so do that now. Okay, so you should be watching the video if you took down my example, if you wanted to, and then you're going to pause the video again and do questions 2 to 7 for me. Okay, pause the video. Okay, so you should only be watching the video now if you have tried to do questions 2 to 7. The answers are coming up, so make sure you've done them. There's no point in waiting for me to do them for you because you won't learn like that. So, okay, this is what you should have done. Okay, here is number 2. Okay, so the substance was copper. It says copper has a melting point of 1085 degrees and a boiling point of 2580. That's what I have here. Oh, I've done them the opposite way here. I've put the words underneath on this one and the numbers above. That makes no difference at all. Same thing. So I've got the melting and the boiling point plotted. Okay, what state is room temperature at, what state is copper at room temperature? I've plotted the room temperature down here. As you can see, room temperature is 21 degrees. It's much below 1085, so that means it will be a solid. Copper is a solid at room temperature. And note the way I have pointed out here what the substance was, so you should also do that. Next one, mercury. Mercury has a melting point of minus 39 and a boiling point of 357. Let's check that I've done that right. Here we go, same thing, solid, liquid, and gas on my number line. There's my melting point, minus 39, and my boiling point is 357. I've written here that it's mercury, so I have it labeled. And I've plotted 21 degrees is higher than minus 39, but it's below 357. So in here, that means mercury is going to be a solid at room temperature. Okay, or liquid, sorry. Apologies, mercury is a liquid at room temperature because it's between the melting point and the boiling point. Next one, we're talking about argon. Okay, so argon here, this is my substance, argon. Argon has a melting point of minus 189 and a boiling point of minus 186. Only 3 degrees in the range there. That means it will only be a liquid for 3 degrees. So very close melting and boiling point there, so unusual. Okay, now I plot my 21 degrees. Well, 21 degrees is much higher than either of these. It's way above minus 186. So that means argon will be a gas at room temperature. Well done if you got that right. Last one of these, cesium. Cesium is an alkali metal. Okay, that means it's in group 1 of the periodic table. And plotting it here, it's got a melting point of 29 degrees. So quite just a little bit above room temperature. So it's almost melted at room temperature. And it doesn't turn into a gas until 685 degrees. Okay, so here's my 21 plotted in the solid portion of the graph. And that means that it hasn't melted yet, so cesium will be a solid at room temperature. Question 6 and 7. Question 6, just to remind us what it was. A substance has particles arranged in a fixed and regular pattern. What state is this substance? You should have said it's a solid. The substance is a solid. And last question. The substance is heated. A student thinks that the particles increase in size. Explain why this is wrong. Well, the correct explanation there is that the student is wrong because the particles of a substance are the exact same in the solid, liquid, or gas states. Gas phase or gas state, same thing. They do not get bigger. What they do is they gain more energy and the spaces between them get bigger. But the particles themselves are identical, they're the exact same particles. So I hope that you wrote something like that the particles don't get bigger, that they just get more space between them and more energy. That would be a good explanation. If not, then you need to make the corrections now. So I'm just going to scroll through these slowly again, and you can pause if you need to stop and make any corrections. Okay, so go scroll slowly. You pause if you need to. Okay, that should do us. Well done. I hope this video was helpful for you. I hope you managed to answer the questions okay, and I'll see you in the next video.